Welcome to this biology webinar session. We'll be going over the first two sections of Chapter 2 in the biology textbook. Be sure to watch our next session about the second two sessions of Chapter 2 in the biology textbook. This chapter is about the chemistry of life. Because to learn biology, we must understand a little bit about the different chemicals in living things. To understand why those chemicals do what they do, we need to start with the very smallest units from which everything is built. Atoms are the tiny building blocks that make up everything you see. Atoms have a nucleus, which we can think of as a ball of particles in their middle, surrounded by electrons that move around the nucleus. The nucleus is made of protons, which have a positive charge, and neutrons that don't have any charge. So when we draw them, we tend to, show two different colors of particles in the nucleus. So here we have blue and orange, and those are the protons and neutrons. The electrons that move around the outside have a negative charge. So this is what makes up atoms, the protons, electrons, and neutrons. And there are different types of atoms. Changing the number of protons in the nucleus changes everything about the atom, making it an entirely different element. For example, an atom with 2 protons is an atom of helium. An atom with 3 protons is an atom of lithium. There will always be the same number of electrons as protons. So there should be a third electron here. Sorry about that. And the number of neutrons also generally increases with the number of protons. But we don't really focus on the electrons and neutrons to figure out what the element is. It's just the number of protons. We call the number of protons the atomic number. Each type of atom is a different element, and each element has a different atomic number. So as a third example, we have carbon here, which has 6 protons mixed in with the neutrons. So carbon has an atomic number of 6. There are 92 different elements found in nature, and each one is made up of atoms with a different atomic number. Remember, atomic number is the number of protons in the nucleus, but what about the neutrons? Are they important too? Well, if two atoms have the same number of protons but different numbers of neutrons, they are called isotopes. Isotopes are still the same element because they have the same number of protons, but they have some differences. When comparing two isotopes, we look at their mass number. This is the number of protons plus the number of neutrons. For example, all carbon atoms have 6 protons, and most carbon atoms have 6 neutrons. The mass number for most carbon atoms then is 12. 6 protons plus 6 neutrons gives us a mass number of 12. But there are some isotopes of carbon that have 6 protons and 8 neutrons. So these have a mass number of 14. And remember, the term that we use to differentiate between these is isotopes. So they're both carbon atoms, but they're different isotopes of carbon because they have different mass numbers. So why does this matter? Well, sometimes having a weird number of neutrons makes an element unstable. The nucleus of an atom breaks down at a constant rate over time. We call these radioactive isotopes. For example, carbon-12 is stable, but carbon-14, with its extra neutrons, is a radioactive isotope. So how do only 92 elements make up the millions of substances that naturally exist on Earth? Because they join together in many combinations to make compounds. A compound is formed when 2 or more atoms have a chemical bond that holds them together. All compounds have a specific formula, a specific number of atoms that come together to make a unit of one compound. For example, water is a compound of 2 hydrogen atoms and 1 oxygen atom. Carbon dioxide is one carbon atom and two oxygen atoms. It'll always be the same atoms coming together to make those compounds. Now, there are two different ways in which atoms can combine to form compounds. In an ionic bond, an electron is transferred from one atom to the other. Remember that electrons have a negative charge and protons have a positive charge. So when an atom loses an electron, it has more protons than electrons. So it has a positive charge. We call it a positive ion. The atom that gains an extra electron becomes a negative ion. Because the opposite charges attract, the positive ion and the negative ion are attracted to each other and stick together in an ionic bond. In a covalent bond, the atoms share electrons instead of them being transferred from one to the other. The atoms stick together because they are sharing electrons. When the atoms come together and make covalent bonds that make them a stable unit, they have made a molecule. For example, water molecule is made when an oxygen atom makes a covalent bond with two different hydrogen atoms. So let's review a few things from section 1 before we move on to section 2. So we have a couple review questions here. Our first one is, what are isotopes? So here's our options. Are isotopes atoms with different numbers of protons and electrons, atoms with the same number of protons but different number of neutrons, or atoms with no electrons around their nucleus? So I'll give you a few seconds to think about that, and then we'll bring up the answer. Okay, so let's go through all of these options. Atoms with different numbers of protons and electrons. Well, those are not isotopes. Those would be completely different elements, because remember, it's the number of protons that tells you what element something is. How about our second option? Atoms with the same number of protons but a different number of neutrons. That is the correct definition for isotopes. And our third option, atoms with no electrons around their nucleus, that actually doesn't ever happen. Atoms are neutral, and so they would have the same number of electrons as protons. So every atom has protons, that means it also has some electrons. If it loses those electrons, we don't call it an atom anymore, we would call it an ion. So that third option doesn't really count as anything that exists. So our right answer there is the second one. Atoms with the same number of protons but different number of neutrons are called isotopes. And that brings us to our next review question. Which of the following are true about bonds? And there is more than one answer that's correct. So I'm just going to give a few seconds for you to think about it again, and then we'll go over each answer and decide if it's correct or not. So our first one, ionic bonds share electrons. Is that true or not? Well, no. Ionic bonds are the ones that lose an atom completely lose an electron completely from one atom, and the other atom gains an electron. They don't share. Next option, ionic and covalent bonds both form compounds. That is true. Covalent bonds share electrons. That is true. Covalent bonds are a type of chemical bond, that's true, and ionic bonds are also a type of chemical bond. So they're both chemical bonds, they both form compounds between atoms, they just do it differently. The covalent bonds share the electron, the ionic bonds, one atom gives it away, the other one takes the electron, and then that makes them stick together. Now, in section 2 is about the properties of water molecules that allow life to exist as we know it. So first of all, water molecules are polar. The oxygen part of the water molecule is a little bit negative, and the hydrogen parts are a little bit positive. Because the opposite charges attract each other, the positive hydrogens in one water molecule are attracted to the negative oxygen in neighboring molecules. Now, this attraction is not like an ionic bond. It doesn't make the atoms permanently stick together in a compound, but they do have an attraction to each other. They do tend to stick together. So the attraction between the polar water molecules is called a hydrogen bond. So this affects a lot of things that water does. Cohesion is the word for the attraction between molecules of the same substance. So because the hydrogen bonds, water molecules are attracted to neighboring water molecules. They stick together. This is why water on a surface forms a droplet instead of just scattering across the top of the surface. The weak attractions between the water molecules cause them to stay together. Water also shows a property called adhesion. Adhesion is attraction toward molecules of other substances. So the polar water molecules are attracted to other polar molecules of different substances. For example, water molecules are attracted to glass. Adhesion and cohesion can work together. So you could have water molecules that stick to their neighboring water molecules, and then the ones on the edge will stick to whatever surface they're nearby. So one reason this adhesion and cohesion are important is because by working together, adhesion and cohesion can create an effect called capillary action. And this is when water pulls itself up through a small channel. So the water will stick to the other material and pull itself up, but behind it, it's going to pull up the other water molecules because they're attracted to the moving water molecules. This happens in a lot of examples that you can see. It happens in fabric. If the hem of your pants touches a puddle, the water will seep up your pant legs. So this is an example. The water might have only been this deep, but the water worked its way up their pant legs, up to their knees. You can also see this in a paper towel. If you have water spilled on the counter and you touch the edge of a paper towel to it, it'll soak its way through the whole paper towel. So those are both examples of capillary action. But it's also very important in biology. It allows trees to get water all the way from the roots up to the top of their branches by the adhesion and cohesion working together. Now, to look at another property of water, we need to know that different substances change temperature at different rates when heat is applied. So for example, if you apply the same amount of heat to a glass of water and to a chunk of metal with the same mass, you're applying the same amount of heat, but the temperature will change a lot more in the metal. It'll change a lot more quickly. The amount of heat needed to raise the temperature of any substance by 1 degree is called the heat capacity of that substance. And water has a very high heat capacity. Okay, so that means we can add heat to water and it doesn't change temperature as quickly as other substances do. So this is actually very important to biology because it allows lakes and oceans to sit outside in the sun all day, soaking up that energy without huge changes in temperature. We learned already that when two different substances chemically bind together, they become a compound. But when two different substances are put together, but they do not chemically bind, they are just called a mixture. Your book describes two different types of mixtures made with water. So the first, when a substance is mixed into water and its molecules are evenly spread out, with water molecules surrounding each of the substance's molecules like this, it is called a solution. An example of a solution is sugar in water. When you stir the sugar into the water molecules will surround each sugar molecule. You can no longer see the sugar. It becomes completely dissolved. There are two different parts to the solution. The substance that is being dissolved is called the solute, and the water or other substance that does the dissolving and surrounds the solute is called the solvent. Because water is polar, it can dissolve other polar molecules or ionic compounds. Water molecules will be attracted to the charges on the solute molecules, so they'll want to come and surround them. Okay, so all of those describe the type of solution called or type of mixture called a solution. The other type of mixture is called a suspension. So in a suspension, the substance added to the water does not completely dissolve. Instead of each molecule being surrounded by water molecules, the substance stays in tiny little clumps, but they're able to float in the water. And an example of a suspension in biology is your blood. Blood is mostly liquid, but it contains cells and other particles in it, and those float through it, and that makes the whole thing a suspension. And water molecules can be broken apart, creating two ions. The H plus ion, called a hydrogen ion, and the OH minus, called a hydroxide ion. If both of those are in a solution, they just recombine and form neutral water molecules. But some reactions create an excess of one or the other to float around in the solution. A compound that releases the hydrogen ions is called an acid, and a compound that releases hydroxide ions is called a base. And we could describe solutions with them as being acidic if there's a lot of hydrogen ions, or basic if there's a lot of hydroxide ions. The presence of either of these ions in a solution can cause different chemical reactions, so it's important to be able to measure the amounts of these solutions. And we do that with the pH scale. The pH scale measures the concentration of ions. The middle of the scale is 7, where pure water with no ions would be. 7 is considered neutral. Going down the scale from 7 is increasing the number of hydrogen ions. Solutions lower than 7 are acidic. Going above 7 is increasing the number of hydroxide ions. These substances are called basic. It is really important that the pH in your body stays in the right range, so that the chemical reactions in the body can happen correctly. Sorry. Okay, so it's really important that the pH in your body stays in the right range so chemical reactions can happen correctly. So there are solutions that help with that. Those are called buffers. Buffers are weak acids or bases that can interfere with the strong acids or bases, keeping them from changing the acidity in a body too much. So now we have a couple review questions from section 2. Our first one, which is true about hydrogen bonds? So I'll give you a few seconds to read each of these options. There's only one true one, so you can figure out what that is, then we'll go over it together. All right, what about the first one? Hydrogen bonds happen because the hydrogen in all water molecules is negative. Well, that one is false. The hydrogen part of the water molecules is actually the positive side. It's the oxygen that's slightly negative. But the second part here, hydrogen bonds happen because water molecules are polar. That is true. So polar, again, means one side is a little bit positive, one side's a little bit negative. And our third option, hydrogen bonds are a form of covalent bond between two water molecules. So remember, the hydrogen bonds are not forming a new compound. They're not a bond where they are permanently stuck together. They are just an attraction between two existing molecules. So they kind of stick together, but it's a really weak bond. And so we just kind of think of it as an attraction between the molecules. And our next question is about pH. So a solution with a pH of 6 on the pH scale has which of the following? So there's more than one correct answer here. Does it have high acidity, low acidity, basic properties? Does it have a lot of hydroxide ions? Does it have a lot of hydrogen ions? So I'll give you a few seconds to think about that, then we'll go over them. So let's look at our pH scale for reference here. So again, neutral is in the middle at 7. We're looking at a solution with a pH of 6. So this is where we're looking. So it's going to be on the acidic side, but it's not a very strong acid. So let's think about these different options. A solution with a pH of 6 on the pH scale has high acidity. Well, no, it's an acid, but it's a weak acid. It has low acidity. And this might confuse people at first because the numbers don't match up with that. You think, okay, a low number, 0 or 1, that would be a low acid. No, no, no. That's just the number it gets on the pH scale, but what it's measuring is a little bit different. It's measuring how strong or weak of an acid it is. So the ones on the edges of the scale, the 0s and 1s, are very strong acids, and the 13s and 14s are very strong bases. And ones near the middle, like 5, 6, 7, and 8, 9, those are going to be weak acids and bases. Okay, so we've got high acidity, low acidity. Does it have basic properties? Is it a base? Well, no, it is on the acid side. How about a lot of hydroxide ions? Well, those are formed on the base side, so no. And a lot of hydrogen ions? Well, I'm giving that one a question mark because yes, it has hydrogen ions. It's on the acid side over here, which means it releases hydrogen ions, but probably not a lot. It's a weak acid, so it's going to be releasing a little bit of hydrogen ions. Okay, so you just need to remember those general concepts about the pH scale, where you have acids, where you have bases, and which ones are releasing hydrogen ions and which one are releasing hydroxide ions.